Thank you, Nick. Good evening. Well, as Nick says, I want to talk a little bit about how we can use some economic methods to measure greenhouse gas emissions in supply chains. So I want to start off with this picture here. And the first question I'd like to ask you is, can you spot the carbon dioxide in that picture? No, it's pretty difficult, isn't it? The other question I'd like you to think about a little bit is, can you put a price on this? Should we put a price on this? Because one of the things that I'm attempting to do is link an atmospheric effect to a price. And I guess one of the basic philosophical questions underneath it is, can we actually do that? Do we actually end up knowing the price of everything and the value of nothing? Okay, I was trying to get 4 C's in here, but I couldn't quite make it. I'm going to talk a little bit about carbon dioxide, but I'm not a chemist, so I'm just going to deal with the essentials as they apply to me. I'm going to talk a little bit about climate change and the potential impacts. I'm going to talk about consumption, and then finally I'm going to deal with economics, which is where my meme doesn't quite fit. So first of all, carbon dioxide. The carbon dioxide series at Mauna Loa has been in place since the mid-1950s, and in May 2013 it exceeded 400 parts per million, which was seen by a number of people as being a very significant number for it to go past. In truth, it's not actually that significant, it's just a nice round figure. But I thought we'd try and get an idea of what 400 parts per million looks like. So that little square is the 400 parts per million of the big square. A few, and there are loads of properties about carbon dioxide, but some of the key matters as far as we're concerned is it's colourless and odourless. And as I asked you earlier on, it's very difficult to perceive as a threat. It's difficult to understand where it is and how it might be around. It's mobile, and what I mean by that is what is emitted here will end up potentially over America or over China, and what is emitted over China will eventually end up over here. And the key to its, or concern about it, is that it variably absorbs radiation. So what it will do is it lets some radiation in, but it won't let that radiation back. This leads to the greenhouse effect, which leads to the warming of the Earth. And initially, it's a good thing because it keeps the Earth at a habitable temperature. The example of runaway greenhouse gas effect is Venus, where the atmosphere is 96% carbon dioxide, and the surface temperature is in excess of 450 degrees Celsius, which is, to say the least, unviable. Okay, climate change. Well, perhaps it's true. It's in the New York Post. It's a very emotive issue, and it's a very complicated issue and a very difficult problem to solve for a number of different reasons. The effects of climate change are quite a long way away. For most of the people in this room, we won't be here to see those effects. And the things that we have to sacrifice in order to do something about climate change are things that we like doing. We like driving around in our cars. We like flying away for our flights, for our holidays. So that means that it's a difficult issue. There's a lot of vested interest. There's a lot of people have a lot of different views upon climate change. So what we're trying to do is to try and bring some numbers to it and allow people to make more rational decisions. I could have shown any number of figures here of the potential effects. I've chosen a fairly straightforward one of the potential effect on global temperature. But we could have chosen increasing sea levels, or we could have chosen decreasing ice levels. But the picture that we're looking at, we broadly agree on, is that between now and the end of the century, there's going to be somewhere between 1.5 and 4 degrees of warming. What will that lead to? Well, these are just a few of the effects, and Hugo is going to touch on one of the more interesting aspects, perhaps, the occurrence of extreme weather later on. But arid tropical regions, areas that we can currently occupy, maybe become unable to be occupied, flooding, warming of the ocean, crop failures, and all of these events can lead to a higher human mortality. There are a couple of upsides to the increase in carbon dioxide, one of which is enhanced fertilisation of plants, and it may be the case that some colder areas are made more habitable. But the conclusion of the Stern review was that, in general, the effects of climate change are going to cost us a good deal of money. Consumption. I guess it's something that we do pretty much every day. We understand what consumption is. Okay, so how about this? Gold-plated Porsche 911. How many of you would like to have this as your ride around town? Maybe we see consumption as being morally something that's unsatisfactory. But consumption and demand drives growth. Many people have been paid to produce that, so they have enhanced their wealth. And one of the other issues we face is the equity issue. Developing nations will turn around to those who are in the north and the hemisphere and who have enjoyed all the benefits of growth and say, why should we hand that back? You know, why should we miss out on that when you've enjoyed it all, just because you've had an attack of conscience about the issue? But it's important to get everybody working together on this because of the global aspect that I was touching on earlier on. People don't often actually think about emitting carbon dioxide. Perhaps if you drive a car, you might think of something coming out of the tailpipe. But could I just have a show of hands as to anybody or people in the room who have estimated their carbon footprint? Okay, so I'm seeing 2 or 3. Okay, so not many people realise what their impact is, what their carbon footprint impact is. But I'm willing to bet that most of you have a pretty good idea of what you've spent your money on over the past month. Maybe not if you've got a girlfriend like me, but it's probably fair to say that that spending leads to industrial activity and commercial activity, and in the course of those industrial and commercial activities, carbon dioxide and other greenhouse gases will be emitted. So we can use spending and understanding how it tracks through the economy to gain some handle on what our emissions are. I was actually finalising this presentation on Friday and watching with some interest the news stories. And this is just one of an image. The Daily Mail provided it happily for me of Black Friday. And I suppose another question I would pose to you is this how we want to be remembered as a generation? Okay, economics. The dry and dusty part of the conversation. Okay, it's possibly a little bit of a stretch to suggest that economists were kicking around in the Stone Age, but I'm sure that people have been interested in how an economy works since very ancient times. I'm sure the Romans and the Greeks were looking at how their society worked and how their economics worked. And the thing is that they have a really bad press. We've just been through a recession and everybody would turn around to the economists and say, well, you never told us about this. You know, you never predicted this. And I think it's fair to say that economics is not good as a prediction tool. But the tools that I'm using are based upon observation of the economy. So it's an empirical method. We look back at how the economy has worked in the recent history. We try and understand the flows of cash between business. And the chap that originally came up with this was a Russian who eventually ended up at Harvard in America called Vasily Leontiev. And he won a Nobel Prize for understanding that the structure of the economy doesn't change much and we can represent it, we can understand how it works. It changes slowly over a period of time. And then another chap called Sir Richard Stone, who was British, came up with a system for national accounts that is rolled out by the UN. So we have a common approach to dealing with the accounts of nations across the vast majority of the world. The model that I use has a very simple, or perhaps it doesn't look that simple to you, but a simple equation at the heart of it. So at the bottom of the equation, we've got, or at the bottom of the picture, we have the equation here. The big red E represents the total emissions, and that might be for a country, it might be for the whole of the world, it might be for a sub-region of a country, it might be for an economic bloc like the European Union. But what we're looking to do is to relate the total emissions of that region to the other factors that we'll discuss as we go through. The second term in the equation on the right-hand side here is some measure of the direct impacts of any given industry. And what we can measure there is the levels of carbon dioxide that are emitted, and we have to relate that back to a financial transaction. So how many kilograms of carbon dioxide are emitted for every pound that's produced in that particular sector. The bit in the middle looks really complicated, but if you want to think of it as a shorthand for the structure of the economy, and it's actually a pretty old concept. This table on the left here is by a French economist called Quesnay, and he came up with this tableau économique in 1758. Now, he only considered that there were two sectors of the economy. The agricultural sector, which he considered to be productive, and the mercantile sector, which he considered to be non-productive. So they basically took goods from the agricultural sector and sold them and made a profit from them. We use something slightly more sophisticated than that these days. So I use a 110 sector model of the UK economy, and I'm currently looking to build up a 48 sector model of the global economy. But the key element to take away from it is that bit in the red represents the structure of the economy and how it all holds together. The final demand aspect is what I use as a variable, and it's what we all have under our control. So this is the measurement of the consumption of goods. And in this case, it's one single figure, but this would be the expenditure on goods in a wide variety of sectors. So if I have a final demand, I could then predict what happens through the rest of the economy. The thing about it is the picture is a little bit blurry. It's not pin sharp, as you can see. We're talking about 110 sectors here. So that means that we lump a lot of products and services together. But what it does allow us to do is to get some idea of the important areas of the picture, some areas that we can focus in on and understand in greater depth and detail, maybe using a different tool set in order to investigate them. It's true what they say, money talks, and I mean this in two different senses. What we're doing here is we're actually following the trail of money through the whole of the economy. That's the first sense that I'm talking about, how we can understand the emissions that arise out of the supply chain. The second way that money talks is in the way that we make our purchasing decisions. So we can have an influence on how our dollars or pounds or euros are spent. And this is an example from my model. So what we're looking at here is how £1 of final demand, the impact it has in terms of kilograms of carbon dioxide equivalent. So there's a little bit of shorthand in there in that We use carbon dioxide to represent all the greenhouse gases, but we express them in terms of carbon dioxide. So it's not just emissions of carbon dioxide. But if we would consider computer, electronic and optical products, and I'm sure that all of you here have bought or will be buying something in this area, for every pound that you spend, we would estimate that around about 30 grams of carbon dioxide are emitted for every pound. That doesn't sound too bad. That sounds pretty reasonable. But when we look down the supply chain at all the economic activity that is generated by that pound, all the industries that have to be stimulated to produce things so that you can have your computer, electronic and optical product, we find that the true picture is a much higher expenditure and a much greater emission of carbon dioxide. So by the time your pound has worked its way all the way through the economy, we estimate that around about 385 grams extra have been added to the original 30 grams. So a total figure of somewhere over 400 grams per pound that you spend on computer, electronic and optical products. To give you another example of something that most people will perhaps have considered buying if they did, or will buy, if you spend £1 in the motor vehicles, trailers and semi-trailers industrial sector, for every pound, around about 43 grams of carbon dioxide. But if you take into account the rest of the economic activity that's stimulated, we're somewhere over 920 grams for every pound. And you think how much a tablet or a mobile phone or a car costs. It's a lot of carbon dioxide. Okay, you'll be delighted to know that we're racing towards the finish here. So there's just a couple of points I'd like to make to finish it all off. I think the important thing here is that decisions that all of us make here will affect carbon dioxide emissions. Now, it's easy to sort of say, well, we can change that, but there are some things that work against us. So we have what we term rebound effects. So even if you decide to take your pound and stick it into the building society or the bank and hang on to it that way, unfortunately, that doesn't mean that it's not actually doing any work, because your bank or building society will invest that money, and so therefore there will be stimulation. So it's difficult to do nothing, but we can make decisions and we can choose to live a lower impact emissions. It's a global thing. So even if we're buying stuff and the emissions are occurring off our shores, we will be impacted by them in the same way as everybody else will be impacted. And I guess what I'm interested in talking about here is the reducing of consumption and the reuse of consumption, or reuse of things. So that's basically my message. I'd like to say thanks to these people here who have sponsored my work and have supported me, and thanks to you also for listening.
Okay, you have to bear with me. This is seamless, absolutely seamless stuff going on here. Oh,
sorry, I should have done that for you.
Oh, it's okay. Control L. Yes, great. Okay. Hello, everyone. So, kind of what I'm going to be doing in my part of the talk is taking on some of the aspects that Robin's been talking about earlier. So he was very much talking about what we can do kind of on a small scale level. So what decisions you can make and how they will affect the carbon footprint. I want to take this on, and I know the title of the talk was, I think, Climate Change Global to Local, or Local to Global. I can't remember which way it was around. So I want to take this on to the global picture. So I want you to start thinking about these kind of claims that are maybe made a lot in the press, and sometimes they can be kind of subverted a little bit when they say, oh, well, in how many years' time and under this level of climate change, we're going to see this many extreme events, so maybe a certain type of event is going to become twice as likely. These kind of things are claimed quite a lot in different areas, so with good scientific grounding, sometimes not with good scientific grounding. So I hope that during the course of this talk, that I can maybe address some of these issues. So my talk is going to be broadly split into two parts. So in the title, Understanding Extreme Events. So extreme events are kind of what I deal with. So types of extreme events like tornadoes, hurricanes, flooding, this kind of thing, so especially from an environmental perspective. But here in a world of uncertainty, so the first part of my talk is just going to talk generally about uncertainty, and that's going to be my pitch that basically, well, I myself am a statistician, and that we are kind of useful at something, but mainly for the from an environmental perspective, it's useful to think in terms of uncertainties when we're modelling. So why do we need to model the weather or the climate at all? Well, I hope this should be reasonably self-evident to everyone here. I'm sure many of you came out this morning and you looked at the weather forecast before you left the house. Do I need a body? Am I going to get absolutely soaked today? We are in Lancaster, so probably yes. Not this badly though. So the first kind of thing I'm going to look at here, these top two pictures show kind of your classic, almost like worst case scenario. So these are disasters that have happened due to extreme events. So a recent example in Somerset was the Somerset Levels flooding. Here there's a picture, I believe, of the aftermath of Hurricane Katrina. So if we're able to better predict when or how often these events will happen, it could be, well, firstly useful from a purely social perspective. The fact we want to avoid as many deaths as possible, that's clearly, but it can also have a big impact economically as well, for not only for companies, but also for kind of governments and the amount of aid maybe they need to give after these events occur. But I didn't want this to just be thinking that we're just simply talking about these really, really bad scenarios here. We're also talking about just everyday life here. So here I've got a nice time-lapse photo of several planes taking off. So basically, the forecasts that are given for at least most flights across the whole of Europe come from a combination of the Met Office down in Exeter and Météo France. And basically, without these forecasts, it'd be pretty much impossible to have the kind of the sheer number of volume of flights that we have now, and with such safety in the aviation industry. So for that reason, it's also important. And I also wanted to draw us also towards kind of the effect that the climate might have on the natural world as well, in terms of so like networks, food networks, this kind of thing, whether certain animals become endangered. Obviously, when I typed into Google search for endangered species due to climate change, you get picture after picture after picture of polar bears on icebergs that are rapidly decaying. So that's what I've gone with. So, okay, so the climate system. What makes up the climate system? Well, there's several different components in the climate system. Here I've just given a few examples, but there are many, many more. And what we can quickly kind of glean from this is that it's a very complicated system. There's lots and lots of different interactions here going along all over. And with each of these interactions, especially when we want to model it, comes some kind of uncertainty here. There's no chance that we're going to be able to take every single atom on Earth and somehow manage to track all of them through time. So we simply can't model this system completely accurately. So what can we do? Well, I'm going to just run through 2 or 3 kind of what I would consider quite important kind of uncertainties we have when doing this climate modelling, and then allude to a few others. And hopefully that should make it clear that it's quite an important thing to think about. So the first simplification is this climatic simplification. So there's an uncertainty here that comes when we try and go from what goes on in the real world down to something that we can run on a computer. So here I have a model of, I believe this is the kind of global climate model that's run at the Met Office. So you have some gridded data here, and the process here, you build into your model as little or as much complexity as you want. So quite a lot of the models that are used at the Met Office are highly complex things. It takes their massive supercomputers days on end to run them. And that's simply, I mean, what we've got now is starting to get a pretty good realization of what generally happens, but it still can be very inaccurate at times. So the hard thing at the moment is how you model clouds. That's certainly something that we're really struggling with at the Met Office at the moment. So there's certainly lots of improvements in recent years, but it's certainly not a done and dusted deal at the moment. So again, I've got another one of these pictures with a nice upward trend. And basically what this is hoping to show is that we also have some uncertainty between different global climate models. So each, so here I think there's a few different ones here. So the black one, I don't know whether you can read, so that's Météo France, for example. I think NCAR is over in America. So there's lots of different centers for climate modeling who each have their own climate models that they run. And then from all of these models, we get some loose kind of ensemble here. Because these are all simulations, and due to the simplification in the previous slide, none of them are going to be completely accurate here. So generally, yeah, you have this uncertainty here that you also need to, in some way, account for. Now, the way that's usually accepted to account for this is doing a kind of similar thing to what's down here. You take a decent chunk of these global climate models, and then you derive your results for all of them instead of just one single result. Okay, so then also there's uncertainty that comes in due to the emissions scenario that we choose. So here's a picture, I think, from the report by the Intergovernmental Panel for Climate Change. And I think, well, if any of you have seen kind of the hockey stick plots and all this kind of thing, then you may notice a similar plot to this. So basically, we have several different scenarios here as to what might happen in the future. So the red scenario, for example, this is denoted A2. What does that mean? Well, that means we have some basically rapid expansion. So there's lots and lots and lots of industrialization, which is pumping loads and loads and loads of fossil fuels into the atmosphere, which is causing a big warming effect. But this can range from there until maybe this yellow one, which is, well, what happens if we were to stop growing? So our emissions were just set at the level they were in 2000. So this gives us this kind of broad range of scenarios over which to get some kind of bounds on the uncertainty. So, yes, so I've given 3 examples there. I give a more comprehensive list here. This was just off the top of my head. So, yeah, I've mentioned a couple here. Well, I won't go into these into too much depth. But I know it can probably make you feel a bit confused, because, yeah, it certainly does me a bit. So what can we actually do in this case to reduce the uncertainty? I've now told you, oh, yeah, there's lots of uncertainty here. But from a practical level, yeah, I can tell you that all day long, but we need to be able to do something about this. So the nice thing is, as I said before, for this climate model choice, we can take an ensemble. For some of these emission scenarios, again, you can just run these simulations from a certain initial condition and just vary these about and get a broad range of general realistic scenarios. And then what I'm going to, well, and okay, we got the point down here that also technological improvements will hopefully help to reveal any things that we don't know, although that can only go up to a point. So what I'm going to talk about now, having talked about that, I'm going to now delve in a little deeper to specifically what I do in my kind of day-to-day work. So kind of in here, so we've got statistical model choice. So I'm going to pick a certain set of models, what will be called extreme value models, and we're going to see how these work. So kind of going over the same thing again, maybe to reinforce, but what's an extreme event? So yes, this was from the Somerset levels flood, so flooding, drought, which is something I have looked at, tornadoes, but also extreme events don't necessarily need to be in the environmental sector. That's something that I've kind of looked at a lot, naturally through my work, but certainly at least part of the reason behind the recession and all the global financial crisis was a kind of inability for standard statistical methods to kind of cope with these extreme losses that we saw. So, why even bother? Why should I even bother considering the extremes at all? So here's some more evidence why I'm a statistician rather than an art student. And then, how about that was to go up a foot then? Well, this would then happen. And that's the kind of thing that we're worried about. We're worried about these events that, and in this situation, would cause a big damage, not only to people, but also for insurance companies. So we need models that can work in this situation, rather than models that are just fixated on working kind of for the average behavior of the river. Also, we need models, so I think Robin mentioned earlier, about empirical models, so models that are based upon the evidence that we've already seen. So these models are usually pretty good, but we need models that can go beyond this. If this was the largest event that we'd ever observed, then we need a model that can extrapolate out to events that we may not have seen before. So, okay, so my work specifically is on heat waves, so I'm just going to give a couple of definitions here. So I was going to say a heat wave, kind of maybe sensibly, is a set of hot days and or hot nights that are associated with some increase in mortality. So what in reality that's going to come down to is some consecutive exceedances of a high threshold. So what I mean is maybe, I think in the UK the high threshold is set at 30 degrees centigrade, again varying across the length of the country. So if you have a set of maybe 3 or 4 days above that level, then that would be a heatwave event. So yeah, so in the middle point I'm kind of trying to stress here that casualties usually happen by heat exhaustion. So this is kind of building up over several days. So yeah, that's what I'm trying to show there with a very hot man. And then here, this isn't the only kind of problem we have. Also, we have these kind of more structural problems with maybe the rail and this kind of things that also can cause disruption. So, sorry, this might get a little technical now. I don't know. We'll see. So I'm just going to define a couple of things here that we'll port through later on. So here, as before, I have my threshold set at a certain level. I'm going to say my event has some duration here and some severity, which is this kind of area underneath here, and a peak value. So from this is, it's possible to have the same severity, maybe having an event that kind of is quite low but lasts a long time, or maybe one that's quite peaked. So maybe more importantly is this notion of a frequency. So that's an event of a certain size happening once in every, I've put T years here. So let's say, do I have it on this? Ah, yes, okay. So the big question behind all this is, how will the behavior of heat waves change with the future climate change? So, will the heat waves occur more frequently? Will they be longer? Will they be more severe? Will they have a higher peak value here? So, I think this picture should hopefully try and illustrate what I was going on about 2 slides ago. So, here, this is maybe an event we see now. So, above 35, well, again, not in Lancaster. Above a certain level, we have the event here, and maybe it happens one in every 30 years. So what are the different things that could happen under climate change? Well, one thing that could happen is this event could just become much more likely. So this event is now happening once in every 10 years, so it's become 3 times as likely as before. Another thing that could happen is the event could stay of a similar frequency, but the event could just get a lot, well, here it's got a bit longer, so it's got longer, and it's also got more severe. Yeah? And then the final one I've got down here, which is kind of a very worst case scenario, is that if our event has become more frequent and has become a lot more severe as well. So that's kind of, if this were to happen, then that would be potentially very dangerous. So, yeah. What data do I have? I'm a statistician, therefore I love data. So we have some daily temperature values for a certain set of years for a grid box centered over Orléans. So I don't know how your French geography was, but I just wanted to say that this is very central France. So yeah, I thought I'd put pictures and data up. Basically what we're seeing in these are 12 different climate models here going from 2006 to 2090, and you'll see on each of them that there's some kind of loose upward trend on all of them, but there is quite a bit of variability around, as you might expect, differing levels of variability. So, I'm sorry, I'm going to show some numbers. Okay, this I was wondering how best to convey this information. So basically, to start with, we're interested in whether there's a change in the frequency of events. So that's whether events are becoming more likely. So what I show here is that, so here, G2006, this is kind of the global mean temperature in 2006. Yeah? And I say, if that global mean temperature increases by a degree, then an event here that happens every so the event that happens every 1 year will increase by about 2 degrees. So, kind of loosely translate that back, is that events will become more frequent. Because if an event that happens every 1 year becomes stronger, then kind of the event of the same strength will happen more frequently. I'm sure I can say a bit more about that afterwards, maybe if you have questions on that. I'm sorry. So the important thing to note is that kind of here, so in the brackets, this is for the whole set of climate models that I am using, so all 12 of them. And in this situation, we're getting some positive increase here for all climate models. So there's a pretty consistent change here saying, yes, our heat waves are becoming more frequent, so they're happening more regularly. But however, this change in, okay, here I'm going to look at severity more than duration. In terms of the change in severity, so the kind of area between the threshold and the points, that's certainly not so clear. So here across our model ensemble, with an increase in the 1 degree, you can't really detect any significant change. So at the end of the day, that puts us in this kind of scenario, at least for this particular data set that I have, that heatwave events are going to happen more often, but not necessarily become any longer or more severe. So I'm going to wrap up now. Yeah, the first couple of points, yes, they're basically what I've said already in the last 2 slides. It's kind of important to remember in this data, so the data that I have were very much strongly forced. So we're thinking that A2 curve, the red one earlier on, that was steep trend upwards. So this was indeed a worst case scenario that I was looking at. But I think the more important thing to take from this maybe is that is the level of uncertainty that we have when we're modelling any kind of complex system. Here I use the climate system as my particular example, but there are many other systems out there where there's a lot of uncertainty. And therefore, statistics has a very important role to play in all these things, and especially environmental modelling. Okay, thank you very much. Thanks for listening.